Ok, 1, 2, 3. Só para dizer, porque descobri que antes do seminário eu tenho que fazer a encantação mágica pelos deuses da burocracia. Segundo a lei da proteção dos dados, essa reunião vai ser gravada. Por favor, desligue seus celulares. Ok, e hoje temos o último seminário, last but not least, seminário do semestre. Temos a honra de prazer de ter o professor Riccardo Sturani. Ele é da Itália, fiz universidade em Pisa, doutorado também, depois trabalhou em Helsinki, em Genebra e em Dublino, depois chegou aqui no Brasil. Antes no Instituto de Física Teórica, depois no Estadual, no Instituto de Física do Rio Grande do Norte, e depois voltou para o Instituto de Física Teórica. Ele é parte da colaboração que descobriu ondas gravitacionais, espero que todo mundo lembra disso anos atrás, que agora virou uma ciência de precisão, astronomia de multiverso de ondas gravitacionais. Ele vai falar disso hoje.
Obrigado, Jorge, pelo convite. Então, já que vai ser gravado, ninguém sabe que vai assistir. Posso falar em inglês? Sim, vou falar em inglês. A benefício de que vai assistir gravado.
Sim. Absolutamente.
Poucas páginas também. Okay, so it's 7 years now, more than 7 years that the first detection has been made, so you must have heard, even if you don't work in astronomy. You're a physicist, so you must know gravitational waves have been detected. So what I'm going to do today is an overview of the observational situation, and then I will flash one slide with all the possible applications of this gravitational wave detection, and then in the last 20 minutes I will focus more on what I really do for life, for living, which is the theoretical modeling. But I will start from the observation, and then I will go up in a hypothetical scale with increasing level of theoretical presentation. Okay, so starting from the very bottom in the sense from the before the observation, we have to decide the detector. So it's an observatory, but it is an observatory which is quite different from the standard electromagnetic observatory. So how do you measure gravitational waves in the lab? Okay, gravitational waves are perturbation in the metric. Okay, I cannot give you a mini course in general relativity, but this is something intuitive. I mean, you don't need to have studied general relativity to at least being able to imagine that the space-time is a dynamical entity. If matter can take curvature into the space-time, it can also create waves in the space-time. And so in this way, in general relativity, it happens that they propagate at the speed of light, or as I like to say, light propagates at the speed of gravitational wave, and then they carry an energy and angular momentum, like any honest radiation. And eventually, wherever they are produced, they can travel at the speed of light. They can eventually reach the Earth. And if at the Earth you are good enough to build this kind of device, you can actually detect it. How? So first, you need an interferometer. The interferometer is the interferometer is a source of coherent light. So a laser is a prototypical source of coherent light. So of course, the standard light is not good because the casual superposition of many different sources, and so you actually what we measure from an incoherent light is just intensity of light. With this source of coherent light, each inch of time and each point in space, light has a different phase. And then you have an splitter, so it splits its coherent beam of light into two beams propagating in degrees. Then they hit the mirror at the end, they come back. And when they come back, they are partly combined, and this is a photo detector. a reader of intensity of light. Okay, there is an animation, but we wasn't able to send it to here. So the idea is that if you change the optical path, you change the relative phase of the two beams when they combine. And the intensity of the combined light is actually a direct measure of the difference of the phase of the two beams coming from the two optical paths. So that's why you need the coherent light, because you're really seeing the intensity of light varying because the phase of the combined light is varying because the position of this mirror is changing with respect to the position. And this is exactly what gravitational waves do. Gravitational waves can change the position of one mirror with respect to the other mirror. So they change the relative phase, and so this changes the intensity of light. The intensity of light is something very easy to measure. So with present technology, one can measure a phase shift of 10 to the minus 8, 10 to the minus 8 radians. So if you consider that the typical wavelength that using this laser is near infrared of the order 900 or 6 meters, and then you consider that the light actually, this is a simplified version of the lights. Light goes back and forth a few hundred times, because there are what are called fabric of cavity. I mean, you can imagine in the first approximation there are just mirrors, fabric reflecting mirrors. And then the photon that goes back and forth has probability to stay inside the arm for several bounces instead of going immediately out. So on average, the bounce, each photon can go back and forth a few hundred times. So this artificially stretch the optical path by a factor of a few hundred without the need to build a longer arm. These arms are physically of few kilometers, 3 kilometers for Virgo, in Italy 4 kilometers for the line in the US. So the optical path is really a few hundred kilometers. So if you take the optical path and the physical difference that, of the optical path, which is the gravitational wave, which is moving this mirror differently from this mirror, and you multiply by the number of bounces, and you dimensionalize by dividing by the wavelength of the laser, and you compare to 10 to the minus 8, then you get the minimal delta L, the minimal differential displacement you can measure. And this corresponds to the 10 to the minus 15 meters divided by the number of bounces. And this is absurd, no? Because what is 10 to the minus 50 meters? It's the size of a proton, of a nucleus of an atom. But this doesn't mean that this device is capable of measuring the position of individual nuclei of atoms. No, forget it. It's capable of measuring, this laser is like this, I mean, basically a few tens of centimeters square when it reaches the mirror. So imagine the average position of the macroscopic part of the mirror to this precision. You cannot measure, of course, the position of individual atoms. Imagine the average position of the mirror to this absurd precision. And in this absurd precision, you think, then you can measure. We know that the gravitational wave, they create a relative displacement between the two mirrors. And so if you divide by n, and you can consider that this is in meters, but the size is kilometers, so by dividing by n, you get a factor of 10 to the 2. Then you have meter to kilometer, you get a factor of 10 to the 3. Then you get to the magic number 10 to the minus 20, which is the typical size that you can foresee to measure with this kind of device. 10 to the minus 10, 10 to the minus 20 is the relative displacement of the two mirrors that you can measure, and it's exactly proportional to the amplitude of the gravitation. So now, one other detail. Of course, you need a differential displacement, no? Because if the two mirrors move coherently in the same direction, then you don't have a change in the phase. You need the two mirrors to move differently. This has to do with the fact that gravitational waves, like the other radiation, the only other radiation we know, electromagnetic radiation, they are boundless. And so, basically, if a wave arrives cutting the plane of the interferometer at 45 degrees, then it will affect symmetrically the two mirrors, then we are blind. But unless the wave arrives in one of these four directions, one direction, two direction, three direction, four direction, unless the gravitation arrives in one of these four directions that bisects the plane of the interferometer, then this interferometer has a non-zero response. So it has an acceptance which is better than electromagnetic, you know, because in electromagnetic radiation you have exactly zero when you have a dipole in the direction of the dipole. This is the quadrupolar pattern of the detector. So, and just to summarize this is the fast. The output of the detector, as I said, the intensity is proportional to the gravitational wave. Gravitational wave comes in two polarizations, like for electromagnetics. Conventionally, they are called H plus and H cross. So the response of the detector needs not to be linear, of course, but since H plus and H cross are so small, 10 to the minus 20 or less, linear approximation is good enough. So we have the output of the detector will be some factor times one polarization plus another factor times the other polarization. So, and these two factors, actually we can take the quadrature sum of the two. This is the value of these two factors. So they are exactly zero, the blue means zero, for these four directions, which are the four directions that bisect the plane of the interferometer. This is for the interferometer in the state of Washington, in the United States, one of the two LIGO. This is for the interferometer in Livingston. And this is for the interferometer Virgo in Italy. And you see, the blind spots for the two LIGO are oriented so to have the blind spots exactly in the same direction. So that if one of the two detectors sees something, then the other detector must also see, unless it's the noise of that detector. So if it's really a coherent gravitational wave that is there, then it must show up in both of the detectors. Virgo noise is oriented differently, so in some sense you can cover some of the direction which LIGO is blind. And of course, for all of the detectors, you have maximal sensitivity if the wave arrives exactly on the top of you or for the bottom, that is completely degenerate. So you see the two maximal sensitivity are the direction exactly on the top or the diametrically opposite one. Okay, so there is a slight modulation with direction in the sky there, but first approximation, these are omnidirectional. Not equally sensitive for all direction, but roughly there is very few, I mean, the region of the sky at which the sensitivity is negligible are very small and very considerable. Okay, and these are real pictures of the interferometers. As I said, these are 4 kilometers. These are really macroscopic observatories. So these are 4 kilometers, and you need to have vacuum in there because if you want to shoot a laser and on 4 kilometers, you want the laser to hit the mirror at the end, you must be sure there's no atom of air in between to scatter the laser. And so here, the laser, the splitter, and then at the end you have the mirrors. It's important that the mirrors are suspended because, of course, you cannot nail the mirror. Because if you nail them, they will not respond to the gravitational wave because they will feel the force of the nail. They must be as free as possible, of course, not in the z direction and when they fall down, but in the xy plane, they must be as free as possible so that they will respond freely to the gravitational wave and their motion will follow the gravitational wave and not, I don't know, the forces or the mechanical forces of the suspension. So, very sophisticated suspension has been developed for this reason. So, this is the summary of the observational picture. So, in the first observation run, the two light as well, and there were 3 detections. 2 detectors that made 3 detections of gravitational waves emitted by coalescing boundaries of black holes. Then there was a second science run that lasted for 8 months, and we only joined in the last month. And there were 3 detections by LIGO only, 4 detections by LIGO and Virgo, and 1 detection in triple coincidence between the 2 LIGOs. And then there was O3, so overall roughly around 10 detections. Then in O3 there were 80 more detections. O3 was split into periods of 6 months, O3A and O3B. And actually O3B lasted only for 5 months because it arrived in March 2020 where everything was shut down, not only LIGO and Virgo, but the world was shut down in March. So now the 2 LIGOs are in data taking. Now, exactly now, you can go, there is a website where you can see live the new events. Of course, there are not one event every second, it's roughly one big event every 1 or 2 per week. And so, Kara is supposed to join, but they are still doing some upgrade. Virgo was supposed to start taking data in May, but they are also doing some upgrade, so they are not started yet. But the 2 LIGOs are on right now. Virgo and Kara will join very soon, and within the end of the decade, there will be an additional detector in India, Indigo. So, what's the game? Okay, this is just a crash course about general relativity applied to gravitational waves, just this slide. Okay, so I already mentioned that the sources of gravitational waves were coalescing binaries. Let me be a bit more quantitative on that. So what is the source? Now for the electromagnetic field, the source of the radiation is a time-dependent dipole. For a gravitational wave, the source of the field is a time-dependent quadrupole. So what is the quadrupole? Is the second moment of the mass. So the mass would be the integral of rho, of the mass density. If you take the integral of the mass density weighted by twice the length, the second moment, then you obtain the quadrupole. This is more or less the definition. And we usually take out the phase because the phase is not responsible of sourcing gravitational waves. So what happens is that the amplitude of the gravitational wave is proportional to the second derivative of the quadrupole, because it is 1 over the distance. You can understand the second derivative just for dimensions, no? Because this is the metric perturbation should be Gm over R, no? Gm over R is a dimensional quantity that tells you how far you are from the cause. But this is not n, it's n times 2 lengths. So you better derive twice with respect to time. If we work in units where the speed of light is equal to 1. So this is dimension-wise is mass. But actually it's mass times n squared divided by 2 times. So it is actually the kinetic energy of the source. So this plays the role of the. If this was the Newtonian potential perturbation, there would be Gm over the distance. G over the distance stays, but then the second derivative of the quadrupole is the symmetric transformation, which is the reduced mass divided by the total mass times the kinetic energy. So the source of the gravitational wave perturbation is not the total mass of the system, but is the kinetic energy of the system, which by definition is smaller than the total mass, no? Because V is always smaller than 1. So you can think, well, but wait a second, all these objects are extragalactic, and these objects are stellar masses. And do you think we can measure the Newtonian potential of a star outside a galaxy? No way, no. Forget even inside a galaxy, which is, if it's not our sun, forget detecting the Newtonian potential of a star or galaxy. And this is smaller than that, because you see the source is the kinetic energy, not the total mass. So how can one be so crazy of even thinking such an experiment? Well, because there is this oscillating factor. So we are not measuring an offset on the top of the gravitational potential of the Earth or the quasi-static gravitational potential of the Sun. We are detecting something that oscillates with a specific pattern. So the gravitational potential of the Earth is 10 to the minus 9-ish. This is 10 to the minus 20, 21, but it has a specific oscillating pattern, which the gravitational potential of the Earth or the Sun does not have. And this is what we can give a hope to measure it, and actually this is what we measure. And then there is this three factor. This three factor is just a modulation. Earlier I told you that the detector has a modulation that depends on the direction, just because it depends on the direction of the arrival with respect to the orientation of the two arms. And this is another geometric factor that has to do with the source, how the source is oriented with respect to the observer. So if you observe from what is called face-on, so if we see perpendicularly to the plane of the orbit, we see two polarizations. If we look parallel to the plane of the orbit, we are killing one polarization. This is written here. If we see at theta equal to 0, perpendicular to the plane of the orbit, the two polarizations are maximum, are weighted by 1. If we see at theta equal to pi over 2, we look at from the plane of the orbit, then we kill one polarization and we kill half of the other. But we don't kill all of the signal. So in this sense, all the sources, no matter how oriented they are, we can see them. This slight modulation depending on the orientation of the source with respect to the direction of the light. This is something different than what I told you earlier, that really had to do not with the orientation of the source, but to the direction of propagation with respect to the effect. So these are the typical order of magnitude of the frequency you get, since we are talking about objects of a certain mass m that are going around each other as a radius r. So you put the radius, typical mass, and you get the frequency. So of course, you enlarge the radius, you go down the frequency. If you keep the same radius with higher mass, you also go up with frequency. But usually, if you go to higher mass, you are also to increase the radius, otherwise the two masses will eventually collide because the size of the black hole is proportional to the mass. So if you take the maximum frequency given by mass n, it goes down with the mass. Just because the mass goes up, the size goes up, And so the frequency of if a bigger object going around a bigger object has to go down because the two objects has to go to a longer path, so the frequency of the object goes down. And this is the maximum frequency that you can have with the solar mass, with the solar mass object. And we know that to have frequency, to have a gravitational wave at this frequency at the Earth of the periods, the object must be compact. Because you can have a subsolar mass object, not like the Earth. I mean, our planet is subsolar mass at this part. It takes a long time because it has a radius of 1,000 kilometers. So no matter how close the orbit with this companion might be, it always has to go at least a few thousand kilometers, just its radius. So this will give a small frequency. So if you want to look at objects at high frequency, which is the frequency like we are sensitive to, you must go to compact objects, like neutron star or black holes. And compact objects do not exist if you have less than 1 solar mass, less than 1.5 solar mass, 1.2 solar mass for neutron star. Unless there are some exotic formation mechanisms like primordial black holes, but I don't want to talk about that. I mean, all the physics I'm giving here is standard GR, solid astrophysics. There's nothing exotic. I mean, this doesn't mean that exotic things shouldn't be studied, of course, but they just don't fit the 1 hour segment. Okay, so this is the typical frequency we are looking at, because why? Well, because light, I mean, the device is what we have, the observatory is what we have, so we better focus on what our observatory can see. Of course, objects which are farther apart, they would emit a lower frequency. They would, but we never see them with this kind of observatories. And so this is the amplitude of one polarization, the other polarization, there is this kinetic current factor, this is one of the distance, there is this geometric current factor, and then there is modulation with the phase during the orbit. And one nice thing is that this phase is a dimensionless number, radians, so if you like, and so it cannot depend on time, it cannot depend on the ratio, time divided by mass. Remember, here I'm using G Newton equal to 1, so the mass is a length. Okay, and the length is time. So time divided by mass is really dimensionless. And so it can also depend on some other dimensionless factor like symmetric mass ratio or the spin divided by mass square. You can check the spin divided by mass square is also dimensionless.
So sorry,
Yes.
G1.
Yeah, I mean, yes, here I use it here. G, you can think of it as a converter from mass to length. No? Gm over R is dimensionless. So G is a converter from mass to length.
Okay.
So since G is converted from mass to length, if I understand G, then this can become a length. That's what people do usually in general relativity.
So this is 1 over epsilon, two positions divided by the planets, basically. Something like that.
Yes, if you want. Yeah, but I found misleading to introduce M-plan because M-plan requires H. Okay, and here everything is classical. You can very well send H to 0 and nothing happens here. But yes, of course, people in particle physics like to express G Newton as 1 over M-plan square. What can we? Fine. So the two polarization, the next thing I wanted to say is this is the time of the source. So you know that in cosmology there is the redshift. Okay. The time measured by the clock at the source is not the same as the time measured by the observer. There is a redshift factor, 1 plus n. So let's introduce the time of the observer, and then this was, you remember, it was Ts, no? The time of the source. Then we paid it for T observer divided by 1 plus n. And so basically the phase, of course, the observer measured everything with respect to the time of the observer. Then you must have this n times 1 plus n. So by the specific shape of the phasing, you don't actually measure the mass. By the specific evolution of the phasing in time, you don't measure the mass, but you rather measure mass times 1 plus n. And so we put the 1 plus n here. So this mass 1 times 1 plus n we measure from the evolution of the phase. So this is measured because of the evolution of the phase. So when you measure the amplitude, you divide by m times 1 plus n, and then what is left is the luminosity distance. So the gravitational wave automatically measures the mass of the object, the mass ratio, so the individual masses, and the luminosity distance. But with a caveat. It doesn't really measure the luminosity distance, but this combination of the luminosity distance and these geometric angles. So if you measure the two polarization, fine. You have two measures, you have two unknowns, angles and distance, you measure the two. But if you only measure one polarization, then you are stuck with this degeneracy. You don't really measure the luminosity distance, but the luminosity distance and the inclination. In practice, this means that if you don't know if the detection was far away but with very good orientation or was nearby with a non-optimal orientation. Okay? If you measure only one polarization. If you measure two, no, you can detect two. The problem is that the two ligons are oriented in the same way. So the two ligons measure the same polarization. Okay, and we measure the redshifted mass, not the intrinsic mass at the source. Fine, with all this introduction, now I can finally give you the observational results. The observational result I usually display in this way is 90 pairs of binary of compact objects. You see, we have two pairs of neutron stars. Double neutron star being a probably black hole, double neutron star being a probably black hole. We have a couple of systems on neutron star black hole, and a couple of systems which are emitidas, because you see the neutron star is really heavy. Okay, this should be a neutron star black hole. But this is really strange, because the light object is 2.6. And we never observe a neutron star with above 2.2 solar masses. You know, neutron stars are very common. No? In our galaxy, there are thousands of them. But unfortunately, almost all of them are isolated. So if you see an isolated neutron star and you see through its pulsar beam, you don't know its mass, because it's isolated. We know the mass of the neutron star only if they are in a binary system, either with another neutron star or with a star. And there are roughly 10 neutron stars in binary with a neutron star and 50s, 70s neutron star in a binary with another star, with a non-neutron star. So if you look at the masses of the neutron star in other galaxies, they are all below 2.2-ish. So this is a problem. Then we say, oh well, but then it could be a black hole. Well, but then we don't see black hole so light either. We don't see black hole below 5 solar masses. And the model, the statistical model of formation of black hole by the collapse of a star requires a lot of gravitational pull to form a black hole, because if the star is too light, typically below 5 solar masses, the supernova explosion is enough to blow out most of the mass, and you are left with none, either a neutron star or none. So you better have at least 20 solar masses in the star to end up with the black hole of 5-ish solar masses. So this point here is a bit of a problem for what we believe we know about formation of compact object by supernova explosion. And then this object is the most massive black hole ever seen. Is this true? No, it's not the most massive black hole ever seen. It's the most massive black hole ever seen in the solar mass machine. Of course, we know black holes which are way more massive than that, no? The Event Horizon Telescope gave us that beautiful picture of a 10 to the 9 solar massive black holes. All of these, they get up to 100 solar massive black holes. Okay, so these are called the solar massive black holes, and there were a couple of black holes that they form an object, a final object with 150 solar masses. This is the heaviest ever seen solar mass black hole, or if you like, the lightest, the first ever intermediate mass black hole. Since it overcomes this psychological barrier of 100 solar masses, we can call intermediate, no? To differentiate from solar masses, which are 10, 20, 30, 40, 60, and supermassive, which are 10 to the 5, 10 to the 6, 10 to the 9. Okay. So all of these 10, 20, 30, 40 are believed to be formed by collapse of massive stars. Black holes of over 100 solar masses might be difficult to accommodate them as collapse of massive star, but okay, we'll see. And then all the supermassive ones, like the ones seen by the Event Horizon, they don't come from the collapse of star, but they come from the center of their galaxy. They collect a lot of stuff and they grow big, cosmologically. Okay, and so. Okay, let me see. So these are the typical noise curves of the LIGO detector. You see there are spikes every now and then when you see the physical sources of noise, like for LIGO, you have the power line at 60 Hz. So at 60 Hz you have a huge spike, and then all these other spikes are the suspensions of the mirrors. Of course, you make the suspension as perfect as possible to shield the mirror from disturbances, but they must have some resonant frequencies, and you just make those resonant frequencies as narrow as possible to pollute as make their pollution in the noise as thin as possible. And this is the amplitude of a bunch of signals. There are 90 signals in a gallery, just plot the sample of them. So this is the binary of star that extends, you see the merger happens out of the band. For all the binary black holes, the merger happens inside the band. And of course, if you move up the masses, the signal moves to the left. Because you move up the masses, the system is bigger, then it takes longer to go around, and so the frequency goes down. So eventually, if you go beyond 100 solar masses, then you're out of the band and you don't see it. Of course, the amplitude also depends on the distance. You change the distance, and then the amplitude goes up and down, of course. Okay, and there is a curiosity, then according to the stellar implosion mechanism that we know, stars of few or 200 solar masses, they should have a pressure at their center so large that the pressure there is capable of producing pairs of electron positons. And so the star should actually blow up instead of collapsing to a black hole. So this should result in a gap of a black hole. So this should result in a gap in the mass of those stars, in 100 to 200. They should translate into a gap in the mass of the black hole between 60 and 80. But we saw one black hole of 60 solar masses, so this is a kind of intention with this picture of astrophysical model of stars. But again, it's one signal, it's a very, very massive signal, which is really in the low frequency part of the noise. You see this signal. We really saw 1 or 2 cycles of this fluorescence, so I wouldn't, trust too much there.
This is not the Schwinger effect, right?
No, this is pair stability supernova. So because you have it impressed not in electric field, but in presence of matter.
And this is chemical, this is an equilibrium, lossing lines and so forth.
I think it's, what happens is that, if you are in this region, if you are in the high mass region, you create electron positons, and then they can escape, or what it happens. And then they drop the pressure, no? When the photon is converted into pairs, you drop the pressure, so it gives you a runaway process. No? Then the explosion of the star. So, okay, I'm not an expert of this, but this is, astrophysics say that this is in kind of mild, just to tell you that in this spectrum, we are in two kind of problem. This is called the lower mass gap. You see a compact object in between 2 and 5 that was supposed to be unpopulated of compact object, because neutron stars are smaller than 2, are lighter than 2, and black holes should be more massive than 5. And we see basically this object here is 78 solar mass, and it's right this way. There is a single black hole of 70-ish solar masses that is right in the gap of this pair instability. But again, this has to do with the astrophysical model of collapse, which are not fundamental physics. It's a beautiful piece of physics, but there are a lot of ingredients and a lot of unknowns there. But just to tell you that there is these two potential problems, but they are not a problem of GR. They are a problem of astrophysical model, and there are a lot of ingredients that you need to add to make astrophysical model, so we'll see. Okay. And this is just to give you an idea of what it does in our organization. So when only 2 detectors see a source, then you have a whole circle in the sky that is compatible with the delay between the 2 detectors. But you see, this is galactic coordinate, so a circle in the sky should actually be a kind of double banana. But you never see a complete double banana because you eventually hit the region to which you are blind. Okay? So the signal cannot come from a blind from the region in the sky where the detector is blind. So these are the typical pattern of sky localization that you see when you detect something with only 2 detectors. If you see things with 3 detectors, then no. You start confining the detection to one dot in the sky. And the typical distances to which we have detected this is for 40 megaparsec, which is the closest object. Just to give you an idea, the typical distances with gases is 5. Average distance between galaxies is 5 megaparsec. The nearest galaxy to us is less than 1 megaparsec, it's 0.7 megaparsec. Of course, the nearest galaxy is closer to the aperture distance. So you go to 5 megaparsec is the nearest galaxy, 20 megaparsec is the nearest cluster, big cluster, then 40 megaparsec is the nearest detection. So it's still kind of locally. And the farthest detection was at around 5 gigaparsec, over a factor of 100 farther away. Of course, you see black holes much farther away, and you see binary neutron star only to your local limit. Okay, these are the rates of the event, which is measured. So these are the rates in megaparsec to the minus 3 per year. So in 1 megaparsec cube, you have a little less than, you have 0.02 galaxy on average. So I told you the average distance is 5. So in 100 megaparsec cube, you have 1 galaxy. So in 1 megaparsec cube is 0.02 roughly galaxies. Per year, you have 10 to the minus 5 and minus 6 events. So per galaxy, you have roughly 10 to the minus, you have to wait 10 to the 4, 10 to the 5 years to have 1 major event per galaxy. And if you look for neutron star black hole, then you have to wait even longer, and roughly the same if you want to wait to 1 binary black hole. You have to wait 1 mega year to have a major event of the binary black hole. Of course, we can see these objects because we are sensitive to extragalactic things. We don't see galactic sources, gravitational wave. And we can see these absurdly large distances because gravitation, we really measure the amplitude. So what we measure was as 1 over the distance, not as 1 over the distance squared, like in the electromagnetism. Okay? And so it's a typical rate of the order of 1 event per mega year per galaxy. Maybe more or because the value of that. And these blue lines were the prediction before the detection. So these were the prediction in 2010. And so you see the prediction were not too wrong. Of course, they span 3-4 order of magnitude. So maybe you might think it's not too difficult not to be wrong if your prediction embrace a factor of 10,000. But still, it embraced what actually we measured. So astrophysicists were not wrong, basically, when they predicted the rates. And this was important because 30 years ago, Kip Thorne had to go in front of a commission of astrophysicists, of real astrophysicists. They wouldn't consider Kip Thorne as an astrophysicist because he was doing gravitational wave. And since astrophysics has been done by humanity since 3,000 years probably, look, you want to convince us to give you money to build an observatory, but you cannot even call it an observatory because we don't believe you will be able to see things. Say, no. I insist that we call it observatory, we call it Laser Interferometer Gravitational Observatory, LIGO. And he basically, this I took from a paper in 2010. So he told in 1990 when he made the case, he probably didn't have this, but probably something equivalent. But of course, you can imagine the skepticism to which this was accepted. But at the end, he kept the case and he got the money to build the detector, and he kept the name LIGO, Observatory, and eventually he was right. So right that he got the Nobel Prize. And now, gravitational wave is a branch of astronomy on equal footing as many others. Okay, and so this is a summary of the rate of detection. You see, first observation run, second observation run, third observation run. You see the slope of detections ramp up when vehicle comes in. Because if you have your detector, even if it's less sensitive, even if it's not oriented in the same way, it has to lower the significance, to hide the significance of the detection. No? If you see a detection, you have to compare it with noise. One thing is to compare with the noise of double detection. One thing is to compare the noise of triple detection. See? When you go to triple detection, basically the number of the background goes down exponentially with the number of detectors. So it helps a lot to increase the background. And so it increases the significance, and you have much higher rate of detection when you have 3 detectors than when you have 2. And this is the plan. Now we are in 4. Vehicles are supposed to join from the beginning of the 4, but they make it. They will join in maybe a couple of months. But LIGO is on now. Kagera, they are still doing engineering of the day. We will be on probably by the end of the day of 4. Of 4 should last 20 months. So it should end by the end of 2024. Then there will be a 2.5 year gap, 2 year gap, and then 5 that will last 2 years or a bit more. So the idea is that we have 90 detections so far, we might have 100, 200 detection, 300 detection here, and basically we should get 1,000 detection by the end of 05, order of magnitude. Okay, and then what's next? After the LIGOs, there will be Einstein telescope. Einstein telescope, so this is the reach, is we can probably read it later. So this is the total mass of the equal mass binary system. So and the total mass goes up to 10 to the 3, 10 to the 4. And this is the reach in redshift. So with the second generation detector, which are the ones working right now, we can barely reach redshift 1. Few gigaparsec is redshift 1 in distance for masses of the order of 100. With ET, which will be basically the same principle of LIGO but underground, and it will be triangular. So basically, by digging 3 tunnels, you have 3 interferometers, 1 interferometer, 2 interferometers, and 3 interferometers. You put it underground. Why? Because there are a lot of vibration that make noise in LIGO and Virgo, but vibration are superficial waves. So if you go underground, you kill this vibration, and so you can see signal at low frequency. A lower frequency than 20 Hz, like LIGO is doing. And if you see signal at lower frequency, then you see higher masses. Okay? Because the mass means large, bigger black holes takes longer to go around. So lower frequency means that you see higher masses, and if you see higher masses, then you see farther. Because higher masses, they are louder, so you see farther. So you can see basically in principle with the Einstein telescope with this third generation detector. Einstein telescope is the project in Europe, and the Cosmic Explorer is the project in the US. You can see up to redshift 100. This is a bit like science fiction, but redshift 20, yes, you can. And this is another project that should be appearing in the next decade. Cosmic Explorer and Einstein telescope should be working in 2020 to 2035-ish. And roughly at the same time, LISA, the space interferometer, should also work. And LISA will be in space, laser interferometer space antenna. And then the laser and there will not be in space, there will be laser and mirrors at 1 million kilometers away. Anyway, you don't have to make vacuum, it will be in space. So you just send 3 satellites and you let them shoot the laser among the 3 of them. And so since it's 1 million kilometers away, then it can experience gravitational wave perturbation at a lower frequency. Lower frequency down to 10 to the minus 4 Hz. 10 to the minus 4 Hz is the inverse of hours. So object with the period of 1 hour. And for instance, we know already that there are objects of period of 1 hour in our galaxy. The binary neutron star. Binary neutron star that we see tens of 10, 10-ish, 12, 8, I don't remember, around 10. We see they have a period of hours. So, but of course, you can also see period of hours of objects which are much bigger than neutron stars. You can see up to objects which are 10 to the 6, 10 to the 7, 10 to the 8 solar masses. Okay, 10 to the 6, we know there is one black hole in our galaxy, but the reach of this object will be basically the entire universe, so you can see supermassive black holes going around each other at basically all of the universe. Okay, and this is another way of saying this. This is the reach of the yellow dots and binary neutron star in redshift scale. This is the reach of Cosmic Explorer at the beginning of this project and Cosmic Explorer at the end of this project. Basically, we see most of the binary neutron star in the universe. And this is the white dot are binary black holes that will stretch up to redshift maybe less than 10. And Cosmic Explorer and Einstein telescope should see most of them. Of course, this relies on the fact that black holes are born quite late in the universe because they come from the collapse of stars. If there are other exotic sources of black holes like primordial fluctuation that collapse in the primordial universe into black holes, then primordial black holes exist at redshift 1,000, 1 million. Then they would be out of reach. But if you, anyway, if you start seeing binary black holes at redshift 10-ish, 12, 15-ish, then it's already a hint that our astrophysical model of collapse cannot account for all of them. Just to tell you one of the surprises you can expect. And so, another way of plotting the same information is this is the redshift distribution of the binary black holes we see now with LIGO. The binary that goes with spectral luminance, the blue line, and green is the binary that goes the third generation detector, cosmic discoveries, will be able to see. So you see, we'll be able to see most of them. Whereas the LIMO, we just see a tiny fraction of the nearby universe. So just to tell you what lies ahead. I mean, if in 10 years if you don't work in gravitational waves, be prepared in 10 years to hear the news about gravitational waves. Or on the other hand, in 10 years, maybe gravitational waves will be so boring because we might have detected millions of them. I mean, who now realize that if there is a new supernova? If there is a new supernova detection, it doesn't even worth a paper, no? You just go to a catalog. There's not a paper for that. Because we have already thousands of them, okay? So at some point, I mean, we are already into that direction with gravitational waves. Okay, and this is a non-comprehensive list of all the new physics you can study with gravitational waves, and we are 10 minutes to the end. So what I want to talk is about precision gravity, but in the next 10 minutes I will give you a hint of how you can do precision gravity with the gravitational wave observations. But before moving to that, maybe it's a good time to stop for asking for questions.
All the collapse, all the stuff about collapse you talked about is sort of from the observation point, there's only if there is binaries, right? No, just to confirm.
No, so the collapse of the star is before the merger, no? Because you need the compact object first. We need the compact object because we are only sensitive to this narrow efficiency. Okay, we are sensitive, yeah, you see, we are sensitive to 20 Hz of the keywords. So we need objects that go around each other at least 20 times, few hundred times per second. And this can only be compact objects. So these compact objects are the result of the gravitational dissipation that make an initial compact object of with a radius like an astronomical unit, million kilometers, 100 million kilometers. They shrink their orbit very slowly because of gravitational dissipation, and this takes 100 million years, probably billions of years, and then they merge, and then we see only the merger when they go.
Okay.
But before they are compact object binary, they must be stellar binaries. Okay, so the star has to undergo supernova explosion. Some of the systems we believe they stay binary, and the explosion doesn't disrupt the binary, at least some of them, and then gravitational dissipation sets in, and then after billions of years, or it could happen that isolated compact object formed with supernova, and then he finds a companion, but this is harder to achieve. Then you need some more sophisticated astrophysical model for an astrophysical object to find a companion in the form of binary. I mean, you know, it's hard in life not to find a companion. Imagine for a black hole in the galaxy. It's basically two objects coming from infinity, they have zero energy. They pass by, they have zero energy, they fly by, and they don't form a bound system. To form a bound system, you need some dissipation to make their zero energy become negative, and this is non-trivial. So the kind of vanilla mechanism for formation of binary compact objects is that you have a binary stars and binary stellar system, and we see plenty of them. Actually, we see 5 or 4 for the stellar system. They go supernova and they stay bound, and then eventually they merge as compact objects. But as you can imagine, it's very, very flourishing the line of research of studying different channel formation of compact objects. There's lots of room for many models. Okay, shall I move on? 5, 4. I move on. Okay, precision gravity. So why we need to model very, very precisely this waveform? Well, because this is the typical, this is the real app. Everybody can download. You can go to the website and download the noise. And download the output detector, which is not only noise, of course, because there is signal, but you don't see light at any time. Why? Because you see there are all these spikes of the noise. If you look at this is the Fourier transform. If you go back to time domain, the time domain is really swamped by this huge distribution of noise. So when you go and download the data and you plot the you see this oscillation, for instance, if you have the oscillation at the resonance frequency of the mirror, those are really dominating. So what you have to do, you go to Fourier transform, then you correlate with the signal you have in mind, because you know the dynamics of a binary system. You correlate, you divide by the noise, so you artificially chop out the content of the correlation, for instance, in this frequency beam, when you have the power line pollution, in this frequency beam, when you have the suspension pollution. And so what is left is the correlation of the least noise polluted part of the signal. And if you get the right signal that might be buried here, if you get the right signal correlated with what is hidden in this huge sea of noise, then you get a spike in the correlation. And of course, you have to get it right also with time, relative time. No? So what you do, you try to correlate, and you see the correlation just noise. Correlate, then you correlate at the right time with the right shape of the signal, then you get this spike in the correlation. And you say, okay, this we call it a detection. Okay. What do we need to model this? So we need to model this very accurately to make the correlation with the signal eventually by the noise. And what do we need to do to model that waveform? Well, first we have to solve for the dynamics of the binary. So we have to know what is but in principle we know, right, the general relativity. So you could say, okay, you throw general relativity to the computer, it's obvious. Yes, but it would be nice to have the analytical understanding what is going on. So it turns out that the two things you know, the two quantities you need to know to pinpoint the dynamic of the source to generate the waveform are the energy function and the flux function, the energy loss function, the EDT. I call it flux. Flux is usually energy by unit of surface, forget it. We call it flux in gravity community, but it's not really flux, it's energy loss. Energy drain. So you see the energy function is minus 1/2 eta, this is the symmetric mass ratio, eta is the reduced mass, this square. So you see this is the Newtonian result. No? The energy of the bound system is kinetic energy plus potential energy. Potential energy is minus twice the kinetic energy, so the total energy is minus the kinetic energy. So this is the Newtonian formula. And this is not Newtonian, but it's the lowest order, is the quadrupole formula. The Einstein quadrupole formula has more than 100 years now, so you cannot call it exotic physics. No? It's very solid physics. So if you have these two functions, then you know how the object shrinks because of gravitational radiation, so you can determine the shape. The problem is that this precision is not good enough. Why? Look at this. What is the phase accumulated by the circular motion? The phase is the integral of the angular velocity. This is tautology. The phase is the integral of phi dot. Let's go one step forward. Let's play the differential. So instead of writing d, we write d, the flux function, and then the d we simplify it from the d from d, and then we get the dv and we integrate the dv. And then omega by the Kepler's law is just d cubed. And here we write the Kepler's law. Frequency of the gravitational wave is linear in omega. And omega is d cubed, apart from the mass in the right dimension, v is the velocity of the binary. And so look at this, v in dv is v to the 1 plus correction. The flux is v to the 10 plus correction. All of these are post-Newtonian correction, or if you like, the general relativity correction to the Newtonian law. And so if you put things together, then you get, and you expand integral, then you get 1 plus c squared plus c4, v cubed, v4, v6, 1 over v6, no? Because this is v to the 10, this is v to the cube, this is v to the 1. And v is always smaller than 1 because it's a velocity. So the point is that if you want to get the phase right, correlate with the signal, you better get the phase with an error less than 1 radians. But look at this formula. In this formula, you have 1 over v to the 6. So unless in this Taylor formula you get also the v to the 6 correct, which is 3pn, the square is 1pn, the 4 is 2pn, the 6 is 3pn. Unless you have the 3pn correct, you get a very poor job in determining the phase to correlate with the data. So this is to tell you that precision gravity is naturally embedded in the analysis of the data that we do. So we have to correlate with the data, and to correlate with the data, the waveform has to take into account the dynamics at least at third post-Newtonian order. So on one end, this is bad because it obliges you to have a precision description of gravity. On the other end, it's very good because it tells you that the output of the detector or the output of that analysis is very sensitive to the detailed features of the dynamics ruling the motion of the source. In that case, we only do this computation in general relativity. But of course, you can think of other theories, but there are absolutely no need to go to other theories because general relativity does the job very, very good. Okay, and so, and then there are a lot of effects that can pop out any perturbative order, like the absorption. The black hole can not only emit, but can absorb because they are black. When the gravitational radiation from the system can go inside the system, then it's absorbed, and then the black hole to some extent can deform. Actually, they cannot leading order, but in the leading order, they might possibly deform, or if on the hand you see some leading order, so the formation is equal to 10, which is 50, but for the order, then you know it's not a GR black hole, because GR black hole doesn't have the formation of disorder, and so on. So you can pull out chirurgically different analytic effects if you have the analytic control of the wave. So, to give you an idea, so the shape of the waveform is always the same, qualitatively. So you have the frequency, the peaks of the waveform goes narrower, the frequency goes up, the amplitude goes up, it reaches a peak, and then you have the merger, and then you have the final black hole that bring down. Qualitatively is always the same. Quantitatively, no. Quantitatively, each waveform inherits the fingerprint of the sources, its masses, the spin, etc. So by doing a exquisitely precise quantitative analysis of the waveform, then we get information of the astrophysical parameter of the source. It can be even more agnostic. You say, oh, well, I don't even want to assume general relativity. I can compute the waveform leaving some parameters of the theory free, and then you can do the same game by fitting astrophysical parameter and fundamental theory parameter at the same time. Of course, at the end, you will obtain loser constraint because you cannot fit GR parameter and astrophysical parameter independently. You have to fit all of them together, but in principle, you can use them. We don't do that. We just fix general relativity, and then we fit the astrophysical parameter within general. Okay, so it's already clear. I can stop here. A few more slides that give you some quantitative details how to compute these two functions. The energy and the flux in some post-Newtonian approximation. This involves particle physics tools that have been developed for particle physics. Already more than 40, 50 years ago. They can be recycled very, very efficiently and very, very well. We don't have to change anything. And so basically we write our Feynman diagrams, we do integration, and then we get those two functions. Yes, we have to compute the Feynman diagram. Basically, we have to expand those Feynman diagrams up to the state of art is now 5 loop. So up to 4 loop, what in particle physics you call 4 loop, is done. 5 loop is almost done. We are struggling to finish 5 loop. And so the basic idea is, let me just explain this one, since there is no form, this is more quality. So basically, in the general relativistic theory, so these are one black hole, and this is the other black hole. Of course, this is the amount of time, and so the two black holes now go around each other and they move forward in time. So in a general relativistic theory, one black hole feels the presence of the other at an earlier time, that feels the presence of the other at an earlier time, and so. So in principle, you need to know all the history of the black holes to know the potential that it feels now. In Newtonian physics, no. You take the potential felt by this black hole is due to the instantaneous position of the other black hole, not GM over R. How the two pictures fit into each other? The two pictures fit into each other. Well, it's the following. Instead of taking into account of all these delays, you can think, okay, in first approximation, instantaneous action distance. I feel your presence there at instantaneous time. Okay, but this cannot be true in general. Right, it cannot be true in general. And indeed, there will be corrections that are related to the derivative of the trajectory of the other eye. So if I'm here, I feel the potential due to the instantaneous position of the other eye, plus correction due to the delay. And the delay are fixed by what? By the derivative of the trajectory. Basically, by never expanding the trajectory, by knowing all the derivative of the other guy, I know all of his trajectory. I assume the trajectory is analytic, but it's a very nice. Okay. So you will find that in this positive framework, general relativity correction are traded for correction on the top of the instantaneous potential, and this correction are dependent on the higher order derivative of the trajectory. And this can be iterated through this mechanism, through these final diagram tools, and as I said, we go to the level of almost 50 perturbative or almost of 5 loop. Some sector of the 5 loop are completely some other. And okay, another thing is that all these loops that we have to compute, I don't know if you have been exposed to final diagram, this is a one loop final diagram, this is computable and it gives a contribution to the classical potential. Then we say, oh wait, a loop is quantum. No, I mean, what George is talking in the particle physics course, that this is quantum correction, is a lie. No, it's not a lie. It's partly true. If you do scattering, this is a quantum correction. But when you want to compute the potential, this loop has a classical part. And the classical part is actually the dominant one, is the only one that survives when you send the masses of these two guys to infinity. When you send the masses of these two guys with respect to the changing momentum to infinity, the classical piece of this diagram is the only one that survives. So this diagram is actually fully classical in the non-relativistic thinking. And this is exactly what we need in gravity. These masses are very large, are huge, these are black holes. And the exchange momentum within them is much less than the rest mass. And in this case, this diagram is classical, and it gives a classical loop correction to the Newtonian potential. This diagram, it also involves two, but you see this is a loop of pure gravity. This is a loop involving the leg of the massive particle. This is a loop involving only gravitons, and this is purely quantum. And quantum physics, I don't want even to hear here. Why? Because these are black holes. This mass is 10 to the 33 grams, and if you convert 10 to the 30 grams with the distance of kilometer, with the velocity of even, I don't know, 1 per minute of the speed of light, then you compute the angular momentum of the system, then you can guess what it will give in terms of h bar. This is 10 to the 7 h bar. Okay? So this angular momentum is really classical, it's huge. And this angular momentum is h bar. It's clear that this will completely swamp the effect of this. We never see this effect in gravitational waves, because this is suppressed by h bar of L. And for us, L is huge. It's astrophysical, it's astronomical. Okay. And without further argumentation. So this was the first time this diagram was computed gravitational physics, and it was like a formal computation that we did originally, and now for loop is not even the same. They are 5 loop, and we are getting there. So these are the different approximation schemes that you use to determine those waveforms. You can use this post-Newtonian perturbation theory. If there are other perturbation theories that involve expanding one of the two masses being much larger than the other. And so you take a Schwarzschild black hole with a test mass, and then you iterate over the range of the mass of the big guy with respect to the mass of the large guy, or you can just brutally use numerical relativity. So you throw everything to the computer and you solve it. This was people have spent decades to get a consistent numerical relativity solution, but nowadays there are codes, not public codes, but there are many codes that can do this. So by, it's a puzzle with different pieces that allows you to construct this waveform. So the one I'm actively in is post-Newtonian is just one of the pieces of the puzzle that allows you to build a description, an analytic description of the analytical numeric description of the waveform. Okay, 5 minutes of the time.
Questions?
No question. In the list that you showed before, you showed the option, the hair of the backbone.
This one? No.
No, in the list of the topics.
Ah, sure. There is one of them you are more interested in.
Or the third one, hair of the backbone.
Ah, inheritance of the black. Yes, in principle, in particular, so when the anime is spiral, the dynamics is a bit more rich. But when you have a final black hole, the dynamic in general is very constrained. You have one final black hole with oscillations. And if general relativity is correct, you should be able to describe all oscillation in terms of two parameters, mass and spin. And in particular, the damping time of the modes, there is a very clean and neat prediction from general relativity of the damping time of all the superposition of the modes you should see. So unfortunately, we have been able only to see one or two modes. But if you could see more superposition of modes, you could check this consistency condition that all of the modes are determined just by two numbers. So since we have seen only two, it's not really a test yet. But if the signal to noise ratio of the fusion detection is higher, we can see not only the fundamental mode, but we can see one subdominant, two subdominant, three subdominant, four subdominant. Then we have a highly non-trivial consistency check of general relativity to fit the damping time of all of these with only two parameters. And so this would be really a smoking gun of general relativity or a variation of.
I actually have a question which sort of, can you go to the Feynman diagram? I know that for example, this one, another one, yeah. I know that in low energy, so the orbit of the moon around the Earth, one very non-trivial check of the equivalence principle is this thing called the Northwell effect. Basically, the inertial, the moon is orbit is elliptical, so the gravitational field in which the moon is different in various phases of the ellipse, and the inertial mass of the moon gets a negative contribution from this. And the question is, does the gravitational mass of the moon change the same way? And if it doesn't, then this was checked with the moon that it does to a good approximation. And at least from the way I understand these things, this is a very non-trivial check of the, it basically says that the second order diagram is.
This is a time to set energy.
Yeah.
It depends on the mass square, but it's only 1 p.m.
It's and it respects the equivalence principle. So the question is, has this check been done with gravitational waves? And
Yes. We've done this, but we've done much more than that. Because you see, with the solar system experiment, you can check only the first Poisson coefficient. Basically, what has been checked with solar system experiment is just this coefficient. Gravitational waves, they fit all the coefficients up to v to the 6 at once. So the precision on each of them is smaller. So the 1 p.m. check from solar system is still better. But for the first time with gravitational wave, we could check V4, V5, V6 that was not possible to check with solar system. So you see, these are the same coefficients in general. Of course, there is the dependence on the astrophysical parameter, which is different. That depends on system by system. But the part of this coefficient that comes from general relativity is the same for all. And we could check this and some higher order. Still, as I said, the 1 p.m. The solar system is still more precise, but in detecting a few more hundred of detection, we should beat solar system even for the 1 p.m. For the 2 p.m., 3 p.m., there were no solar system bound, we are only gravitational wave bound.
Now, has everyone made the catalog of like terms which possibly violate the symmetries of general relativity?
Yes.
Here.
Yeah, in the not way, yeah, this review by wheel, no standard review by wheel. We made a catalog of all the terms that violate it. It's called parametrized positorium. So it's a positorium that doesn't come from a theory, it's just parametric.
Further questions?
Yeah, no. Sorry, maybe you are intimidated by English. Sorry, I just speak English for the recording, but you can speak. You can ask the question.
I have a question from the first part. The number of expected detections and the overall angle precision that you get from a cosmological point of view, how good would be this as a mapping tool, for instance? Will it be more close to supernovas where you don't really get much precision needs, or will it be compatible with the
So you mean for cosmological applications?
Yes.
So for cosmological, there is the one major cosmological application. I haven't talked about it, but I have a spare slide. I put that in the spare slide. So look at this. This is the measure of the Hubble constant with the CMB is the pink one. The pink line with the supernova is the green line. Okay, I went well on these two measures. I assume that you know about these two measures of the Hubble constant. The fact that there has been one detection of a binding neutron star with the electromagnetic counterpart, so we have measured the luminosity distance with gravitational waves. with a large error because there was this degeneracy with the orientation angle. And we measured the redshift because we knew exactly the source, the galaxy. So this is the black line is the measure of the Hadron constant with this gravitational wave event for which we knew the redshift. If you don't have electromagnetic counterpart, then it's a problem because gravitational waves don't give you the redshift. So you have the distance. How do you measure H0 if you don't have the redshift? But if you have the electromagnetic counterpart, then you have this with that, you can measure that. The problem is that the error is large because, as I said earlier, we know the distance, but we know this combination of distance and angle. So we don't know if it was far away and perfectly oriented, or it was closer but not well oriented. We assume that if we see more of this, it's called bright standard siren. So standard siren because they have a standard calibration of their amplitude. Sirens because we make the metaphor of the sound because they are not visible, and bright because they have an electromagnetic counterpart. The idea if you see more of this bright standard siren, which we measure the luminosity, distance, and direction, then this error, this black curve, which is the PDF of H0, will shrink. So with 50-ish bright standard sirens, we should reach discriminating power between Planck and supernovae. Was it the question?
Not exactly, but it's good to know. Without detecting light, suppose you don't get light, you will have still the luminosity distance and the angle, more or less, I guess, with the location in the sky.
Yeah, the location in the sky, yes.
And you have a big number of events. So
Yes.
you will have sort of a map of the
Yes.
source that are produced. Is the number of detections that is expected in the next generation that you mentioned?
Yeah, in the generation will be hundreds of thousands.
Yes, 100,000. So will it be like competitive with galaxy surveys, or will it be much less?
Yeah, okay, it will be better than surveys on the galactic plane because gravitational waves, they go through the galactic plane. So beyond the galactic plane, there will be the only probe, gravitational waves. About surveys, you see, the surveys are, they see, electromagnetic surveys, you see, they look at the intensity, so it goes down with the square of the distance, so they can hardly go beyond a few gigaparsec. Whereas for gravitational wave, we can go to redshift 20 and see, we really see individual object at redshift 20. So there will be, we see farther away than even Euclid. But we are limited to those events that they merge. So we won't see all of the galaxy because for each galaxy you expect less than one event per million year. So in some sense it will be better, in some sense it will be worse, but it will be really complementary.
Further questions?
I have one about the last time, the last section. You mentioned that there is no interest in looking for events that are not like close to general relativity. So there is.
No, I'm not doing that. There are a lot of people are doing, not me.
Because you mentioned that you convolute the signal with some pattern.
Yes.
So is there any other possibility of wave like the signal that's not on the compact object regime that maybe could be created and moving forward?
Yes, but it would be very exotic, because we really see the merger. And we know that if this other object, which is not a black hole, if it gives a signal like this, it means that it has a size roughly the size of the black hole. Because we really see the two objects, the signal is really what you expect in general relativity up to the very end. So if it was a fatter object than a black hole, then it's already ruled out, for instance. So that's why I think you really need, if you want to go out of general relativity, you must be really fine-tuned to something with that. So I don't really see the need. A lot of people are doing that, but frankly, I don't think it's really motivated at this moment. Maybe when we go to higher precision, then we see some deviations. But at the moment, the problem is that suppose you have a different theory and you want to model the signal. There is this fundamental degeneracy because you don't know the intrinsic parameter of the astrophysical source. So you can always skew the astrophysical parameter and introduce some different fundamental physics parameter just because you get some different astrophysical parameter, but what do you learn with that? So at the level we are now, I don't think it's a particularly instructive exercise to do. with LISA, with ETA, when we see signals with signal to noise ratio 1000, so we see really clean, very, very clean signal, so we see a lot of details, then there you will be able really to pinpoint what is astrophysical, what is fundamental, maybe, hopefully you will see some deviation from GR, that would be very interesting. But at the moment, there is zero clue that you need anything different from GR. You might need something a bit more exotic in astrophysics, as I know there are those little outliers in the mass distribution. Those are a bit suspicious, but those seems have to do more with our incomplete understanding of astrophysics rather than general relativity. But again, I mean, one has to be open to surprises, of course, and one cannot go on with prejudices. The point is that you cannot ask to fit too many things with little data.
I have one question comment that since you mentioned my particle physics course, and there are also some students here from the course, this thing about the Feynman diagrams again, that they can be classical. I mean, what we teach in particle physics is that we draw all possible Feynman diagrams, then we, for a given process, then we sum them together and then we square, and there is interference. So here you don't square anything.
No.
That's the question.
No.
But there are situations where you have equivalent Feynman diagrams. I mean, here you have two, because you can have that thing pointing this way, and you can.
Yes, but at the end of the day, these are, you can see these in starting attributes, but what we are looking interested in is how they affect the potential. And so the potential is linear in starting attributes. The potential is really observable.
Because these two objects are classical, they're not
Yes.
momentum eigenstates. That's
Exactly.
really happens.
You have a black hole, and here black is going horizontally. So one diagram is starting here, one diagram is starting there, and they exchange some gravitational mode to bend each other trajectory.
Sure.
So we are not interested in cross sections, but we're interested in potentials, in modification of the potential, and the potential is the Fourier transform of the amplitude. So it's linear there.
No probability in an outstate solution.
No, yes, we keep calling emission amplitudes, which is a bit of inaccurate, talking about classical physics, but you know, since the tools we are using are borrowed from Instituto that has been developed for particle physics, I think this is a forgivable use of language.
So for people, this is like the difference is the in and out states. But it's actually the level of field theory, what is classical and what is quantum, kind of depends on the order you calculate and what you want to see. And this is, yeah.
Yeah, actually, no, in astrophysics, if you really want to be picky, you have to work in the in form, no? Because you specify the state at the beginning, and then you let the ball. But you don't have the factors at the beginning and the end. It's to select your state. But okay, this higher order offer.
Okay. Further questions? If not, thank you very much. We continue next semester, I don't know on what day yet. Vamos ver quem tem carga de